Let's take the topic, half-life of a radioactive substance. First, we take the definition. The half-life of a radioactive substance is defined as the timetable for it to decay to half of its original mass or number of atoms. Now the symbol we use to denote the half-life is denoted T. That is capital letter T. We take the first example. It takes 6 years for a radioactive element to decay from 32 grams to 4 grams. Calculate the half-life of the element. Now the question says, it takes 6 years for a radioactive element to decay from 32 grams to 4 grams. Now calculate the half-life of the element. A solution to this question. The first thing we do is to put down what is given to us. So we write given. T is given as 6 years. The original mass given to us is equal to 32 grams. Why? The mass after 6 years is 4 grams. We are required to find the half-life. That is the time for 32 grams to decay to half of it. And the half of it we know should be 16 grams. All right, let's look at the formula. The formula says that it is 2 raised to power T all over capital T is equal to M naught all over capital M. We now substitute our values. And so we write 2 raised to power, the small letter t is 6 years. And so we write 6 divided by, the capital letter T is unknown to us. And so we just retain the symbol T. Is equal to the mass M naught is 32 over the mass that remains after 6 years is equal to 4. So we put 4 there. Next, we write 2 raised to power 6 over t is equal to 32 divided by 4, and that gives us 8. So we write 8. From the previous steps, we have 2 raised to power 6 over t is equals to 8. Now we can express 8 in powers of 2. And so we have 2 raised to power 6 over t is equals to 2 raised to power 3. It follows from this identity that 6 over t is equal to the 3. In other words, since the base here is 2, the base here is 2, we just have to equate the powers. 6 over t becomes equal to this 3. And that is what we have written down here. Then the next step is to express t in terms of the two numbers 3 and 6. Or let's put it this way, is to make t the subject of the formula. And so we write 6. So to make t the subject of the formula, we multiply both sides by t. And we have 6 over t times t is equal to t times 3. That now gives us 6. For this t cancel the denominator t, we have 6 is equals to, then t times 3, we have 3t. The last step requires us to divide both sides by 3 in order to make t the subject of this step. So we say 6 divided by 3 is equal to 3t divided by 3. Alright, from the previous steps, we have 6 over 3 is equals to 3t over 3. Now if we cancel out, we have 2 is equals to what? T. Therefore, we say that, therefore, the half-life required is 2 years. radioactive element has a half-life of 2 hours. If there are 1,000 atoms in the element, calculate the number of atoms remaining after 4 hours. The solution to this problem. First, what is given to us? We have been told that the half-life is 2 hours. And then the time it decays is 4 hours. The number of atoms given is 1,000 atoms. Atoms. We are required to find the number of atoms left after 4 hours. To do so, we begin with the formula, which is 2 raised to power t all over t is equal to m naught all by n. Alright? So 2 become 2 raised to power by 4 divided by the half-life 2 is equal to the n naught, which is the number of atoms. The number of original atoms is 1,000. So we write 1,000 divided by, as for the mass, we do not know it. In fact, that is what we are looking for. So we write capital N here. So next, we have 2 raised to power 2. For 4 divided by 2, that gives us this 2 here. Is equal to what? 1,000 divided by n. So therefore, now have 2 raised to power 2 is equal to 1,000 divided by n. Alright, 2 raised to power 2, that gives us 4, is equal to 1,000 divided by n. Alright, we cross multiply, it becomes 4n is equal to 1,000. And next we divide both sides by 4 in order to obtain n. We have 4n is equals to 1,000. Divide both sides to divide both sides by 4. So here then we have n as 2, which is 250 atoms. Thus you see, thus the number of atoms mean after 4 hours. It's 250 atoms.